some tests that we can do on orbit later this week before, we discard the service module, so we have a pretty limited window if there's anything we want to do before that happens. So like I said, not sure on root cause yet, but that's kind of how, at a high level, that's how I hope that helped.
Yeah, and Bill, one more point here. In your house, a light switch or a circuit breaker, that is the command device. You literally flip the switch and it closes the circuit, and that is the action or the command that does it. What is a little bit odd to us is there's no record of a controller on board the vehicle sending a command to open the latching current limiter. So in your house, the device is the command object. In this case, there's a separate controller that tells the current limiter to open or close, and there's no record of the command device saying you should open or you should close. This thing is just open or closing without this box, the command device, telling it to do so. So there's some anomalous behavior here that we're trying to understand.
Our next question comes from Gina Sensuri with ABC News.
Thank you very much. Can you just run through the numbers for me? Speed on reentry, temps, all of that stuff. Give me those numbers if you don't mind.
Yeah. Sure, Gina, no problem. So when we come into entry interface, we're at an altitude of 400,000 feet, and we're traveling approximately 24,529 miles per hour. Once we get to skip apogee, which is about 7 minutes 19 seconds after entry interface, we're at an altitude of 291,382 feet, and we're traveling at 16,824 miles per hour. At 150,000 feet, we're traveling approximately 8,547 miles per hour. At 100,000 feet, we're traveling 2,398 miles per hour. At 50,000 feet, we're traveling 528 miles per hour. And when we jettison the forward bay cover at approximately 22,845 feet, we're traveling 285 miles per hour, and then our main shoot deploy is approximately 5,320 feet, and that's we're traveling 128 miles per hour. Then we hit splashdown approximately 20 miles per hour.
And just to add a point here, Judd, I think you said 16.8 is the skip apogee velocity. 16.8 is just shy of what a spacecraft comes back from low Earth orbit at. So that's our second dip into the Earth's atmosphere, is about what a low Earth orbit vehicle would come back at it, which is 17,500 miles an hour.
Our next question is from Brett Tingley with Space.com.
Hi, this question, I guess, is for Melissa Jones. It was mentioned earlier in this conference that there's still a pre-planned decision gate ahead that will help select the landing site. I'm wondering, by what metrics or what criteria are the different landing sites selected?
So that's actually something that Jed Freeland and myself work on together, and it's mostly based on weather from my perspective, and there's, I'm sure, many other factors from the flight side. Jed, I don't know if you want to add anything to that.
Sure, Melissa. So we have a designated primary site that we try to land at first, and that's called San Diego Site 3. That's within the Fleet of Hot area, which is the fleet training area. Hot as in hot munitions. So that is controlled by the Navy. So that's our first target that we try to land at, assuming that the weather and criteria is all favorable, not only for the hardware of the capsule, but also for Melissa's team to recover the capsule once it's in the water. And then we have various other sites within, as I mentioned, that northern weather alternate that we could potentially go to within the San Diego area if the weather happens to be better than our San Diego Site 3. And then if none of those sites look good to us, then we can always go further uprange along that track, that kind of south to north track that I showed you in my previous chart, anywhere Right, that's the one. So you've got a short distance there that's around 1,200 nautical miles that we would still be able to get our skip entry objective for the flight, and then. The only reason we'd go any further uprange of that is if we had something wrong with our navigation system. We had inertial measurement units. If we had more than two or more down, then we'd either do a ballistic or direct entry. So all that to say, we look at the best weather along that track, and we find the best weather. If that best weather happens to be San Diego Site 3, we'll go there, and otherwise we'll find a better place to land within those criteria.
And maybe expand on the weather just a little bit. It's wind speeds, but it's also wave height, wave period, because as we hit the water, how the capsule actually impacts that wave, where its height is, what you're on the back side of the wave, the front side of the wave, how the winds all respond. So it's a pretty complex set of parameters that we look at to say that you need to stay within this wave height, this wave period, this wind speed. So that's how all that plays into where we finally select where to come down.
We do have another question, this time from Alan Boyle with GeekWire.
Thank you. I guess this question would be for Debbie. It's about Callisto. Can you say anything more about the performance of Callisto? And is this something that you've decided could be used on Artemis II, or do you have to wait to see what the performance is and what the objectives are for that kind of communication system?
Yeah, so first of all, in performance, so far it's been really great. I've got to witness several of the sessions. Very, very interactive, very engaging in terms of being able to talk to the spacecraft, turn lights on and off, write notes, play music, ask questions. It's a really very good engagement opportunity, and I think it has some potential on how we would use that further as a digital assistant or some other onboard activity. There isn't any specific plans for Artemis II yet. We're waiting to get back the data from this flight to see, how it worked and what we can learn from how it performed. But so far, the performance has been really, really nice.
Our next question comes from Jim McDade with 1819 News.
Congratulations on breaking so many records on this mission. It's been spectacular. First of all, I'm Jim McDade, 1819 News and Verity Space News Clearinghouse. Apollo 13 set the reentry speed record back in 1970 after it got on its free return trajectory. And I'm given to understand that will be one of the last, if not the last, records that this Orion, that this Artemis I mission and Orion will break. Will future reentry velocities be comparable, or is it possible there will be even faster? Or is this another example of you pushing everything to the limits in this shakedown cruise?
Let's see. So I'll answer that one. My expectation is that the future missions for Artemis will be similar speeds to what we're entering here, if not less. It's all going to depend on the specific trajectory that we fly, and of course those are still being developed for individual missions, but my expectation is that they will likely be no larger than the speeds that we're entering for Artemis I.
Yeah, I think we definitely have some limitations or requirements on our heat shield, and so when we look at the reentry, part of the skip reentry is getting us slow enough down so that the heat gets down. So I think when we look to futures, I know we're trying to expand the skip distance for future missions, but I don't think that's going to affect the speed much.
Our next question comes from Sophie Sanchez with Cosmic Chicago.
Hi, thank you for taking my question. My question is for Debbie. You mentioned a couple of system configurations set for Artemis II that you've already tested. I was wondering if there were any that you were planning for the duration of the mission on the return home, any systems that you were planning on testing for at the Artemis II settings? Thank you.
I don't know specifically if we're testing Artemis II settings on the way home, but there's a lot of things that we are testing so we can expand the operating box that Artemis II can operate in. So things I mentioned like the solar array modal survey, understanding how the solar arrays degrade over time, these pressure control assembly within our prop system, leak checks, how do valves behave over time. This OMZ, we're orienting to tail to sun directly to see how we can get more performance out of the engine. There are some mixed string RCS firings we're going to be doing on the way home. So there's a lot of objectives, not specifically putting things in Artemis II configuration, but driving the system beyond maybe where we thought we were going to operate for Artemis I so we can expand that box.
And Debbie, I'll add to that. This is really the start of a campaign of several missions to get humans back to the moon and beyond to Mars. For Artemis II, there's still a lot of things still to test for Artemis II. We don't have a life support system on Artemis I, and so that's going to be the major objective for Artemis II is to test that life support system. We'll also be testing rendezvous prox operations. In other words, rendezvousing with another vehicle when we rendezvous with the interim cryogenic propulsion stage on Artemis II. So there's still a lot to be done, and this is just the beginning.
Yeah, and Sophie, I'll just give you two more as part of a preview for entry, descent, and landing day that we're planning for here on Artemis I, and I think both these happen on Judd's watch operationally. One is an aerothermal test during the entry, descent, and landing, where we deliberately fire all of the reaction control system thrusters in various points during the reentry profile to gather hypersonic aerothermal data as we fire those thrusters, and then post splashdown, we're deliberately going to keep the vehicle powered, assuming the vehicle's healthy, for 2 hours after splashdown to understand how much heat has soaked back after that peak heating of up to 5,000 degrees Fahrenheit outside the vehicle. As the heat shield protects the vehicle, there's still going to be heat that soaks into the structure that is the Orion capsule. It'll splash down in the ocean. The ocean's going to cool the vehicle, but some of that heat is going to be resident in the structure of the vehicle. So we want to understand how hot the cabin's going to get. So we'll leave the vehicle powered for 2 hours, keep it on the cooling system for 2 hours to understand for astronauts on the very next mission what the temperature profile in the cabin is going to look like. So that's part of that 6-hour recovery time frame that Melissa highlighted earlier. We're deliberately going to wait for 2 hours with the vehicle powered on the surface of the ocean. So those are some of the things that are ahead of us as well.
And that was the final question that we received this evening. So thanks to all who submitted questions, as well as our briefers for joining us in a busy time. Next up, we continue to look forward to Orion's return home. We'll have another briefing this Thursday at 4 p.m. Central, where we'll go over that return in a little bit more depth. And we'll also be covering Orion's entry, descent, and splashdown beginning at 10 a.m. Central on Sunday, December 11th. But until then, be sure to follow along with our daily blog posts as Orion continues its journey home at blogs.nasa.gov/Artemis. Thanks again for joining us. That will wrap up today's briefing.